Hey everyone, welcome back to Calculus 2. This will be lecture 6 of the course. In this section we're going to get into something called numerical integration. So as we'll see, and increasingly as we learn more and more integration techniques, there are going to be many elementary functions that do not have antiderivatives that are elementary functions. And so the question of how to calculate integrals or estimate integrals in those examples, in those scenarios, is going to be the subject of this section. So let's jump into it. Let's go ahead and call this section 1.6, and this will be numerical integration. Okay, so as I was saying, there are going to be countless examples of elementary functions whose antiderivative we're not going to be able to identify. For example, here's an example: cube root of x times the square root of 1 minus x. Okay, so there are no elementary functions that have this as its derivative. And so that means, what that basically means is that the integral of the cube root of x times the square root of 1 minus x dx cannot be easily identified. Okay, so basically we won't be able to calculate explicitly what this indefinite integral, we won't be able to evaluate it explicitly. And so other examples, there's lots of examples. A couple of other examples might be things like this: square root of x times the cosine of x. This integral cannot be easily identified. Same thing with the integral of cos x over x. Cannot be easily identified. 1 minus x cubed square root cannot be easily identified, and so on. So there's lots and lots of them. Some of these, cosine of x over x doesn't seem like it's too crazy of an integral, but it's a definite integral that the antiderivative is not easily identified. And so whenever we encounter a definite integral involving a function like these, where the antiderivative cannot be found, whenever we come across this kind of situation, we basically will have to resort to a numerical approach. So examples like these can only be dealt with using a numerical approach. Now, so don't be discouraged. In general, integrals like this have to be dealt with using numerical approaches. But there are as it turns out, there are very sophisticated numerical methods. There are entire courses basically called numerical analysis, that kind of stuff, that basically explore these approaches and from which you can learn exactly how to calculate these types of things efficiently. So we're just going to touch on a couple of ideas from numerical analysis, numerical integration in particular. One way to approximate a definite integral is to use trapezoids, and that's kind of where we'll start. So one way to approximate a definite integral is to use n trapezoids. Yeah, we might have talked about trapezoids earlier in the course. So the integral from a to b of f of x dx represents the area between x equals a, and x equals b, and under the curve of f of x, right? So we know this. This is just kind of, we're kind of revving our engines here, getting ready to talk this through. But let's say you've got some function like this, right? And you can draw your a, b region, right? And then you can imagine just kind of breaking that region up into equally spaced intervals. Okay. So the integral here tells you, precisely what's underneath the curve. What we've kind of been talking about how the integral is based on an approximation that becomes precise at the limit, right? So what we're going to do is kind of explore one of those methods in a little more detail and spin up some really nice theorems. So let's go back through this. So how to approximate this? Okay. So of course we want to start by partitioning the interval AB, the closed interval AB, into n subintervals, each of width delta x equal to b minus a over n, right? Equal widths, okay, for each of them. And so that partition would probably look like a equals x0 less than x1 less than x2 less than dot 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 less than xn equals b, right? So there's your partition. Okay, and then what we want to do is, and kind of see it up here, we want to form just a trapezoid, right? So you can imagine here the vertical lines are parallel, and then the horizontal line, this one is a right angle with the bottom two, but this one could be anything. Same here, same here, same here, right? So you've got these trapezoids that are implicitly formed. Okay. So step one, to generate the partition. Step two, form a trapezoid for each subinterval. Okay, we'll talk about what we mean by this quick in a second. Before we jump into that, let's talk about what the area of a trapezoid is in general. Let's just refresh people's memory in case they don't recall. So a trapezoid can look like this. Okay, so you've got your A and your B, and there's some height. Okay, and the area of this figure is, you add the two parallel edges up, A plus B, and then you multiply that times the height and divide the whole shebang by 2. Okay, so it looks like this. Okay, so this is the area of a trapezoid in general. So then what we want to do is we want to think about what these trapezoids are, right? So let's say this height here is f of, I'm going to flip to another page. Let's go to the next page, and we'll just redraw this. So let's take our first trapezoid here. Say it kind of looks like this. Okay. And so again, this is just me kind of mocking up this guy, this one here, this one right here. Okay. So the first trapezoid would look like this, right? So here's your x0 and your x1, right? And then the height is f of x0 and f of x1. Okay. Okay, so really what you want to do is you want to kind of imagine this on its side. So in our previous generic example of the trapezoid, we had A, B, and H. We said the area is A plus B times H over 2. Well, let's take this guy here and write it on its side. So it's going to kind of look like this, isn't it? So then this side here is f of x0, right? This side here is f of x1. Okay, then the height, what's the height here? the height is delta x1, right? No, they're all delta x, so we'll just put delta x. Okay. So this is basically what our first trapezoid would look like, right? And so we could say cleanly that the area of this is going to be equal to f of x0 plus f of x1, and then that whole thing times the height, which would be delta x, and all divided by 2. Okay, right? So this is just simple kind of just some basic algebra so far. Let's write that slightly differently. Let's write it like this: 1/2, and then we're going to put our f of x1 plus f of x0. And then instead of delta x, we're going to write b minus a divided by n. Okay. All right, so our first trapezoid would look like this. This is the area of the first trapezoid. The area of the second trapezoid would have the same form, right? It's just going to be f of x2 plus f of x1 times b minus a over n, right? And so on, and so on. The nth trapezoid would be 1/2 times f of xn plus f of xn minus 1 times b minus a over n, right? Okay, and so this could just, we can continue this on and on. So let's figure out the area, the entire area under the curve then, the total area. Okay, the total area is just the sum of all of these things, right? So it'd be a1 plus a2 plus dot 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 plus an. And so you'd have to write it like this: 1/2 f of x1 plus f of x0 times b minus a over n plus dot 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 plus 1/2 f of xn minus f of xn minus 1 times b minus a over n, right? So all n of those are in there. Okay. Now, something to note, you can't really see it easily in this sum just because I didn't put the second term in, but you can imagine if you just look up here, this total sum here is going to have f of x1 in there twice, isn't it? And f of x2 in there twice, and f of x3 in there twice, and f of xn minus 1 is going to be in there twice as well. The only two terms that are going to appear once are this guy here, f of xn, and the first term, f of x0. So let's write this, let's kind of simplify this and kind of pull it all together. So we can pull, each term is going to have a b minus a over n and a 1/2, and so let's pull those out front. So we'd have b minus a over 2n, and then it's going to be f of x0 plus f of x1 plus f of x1, so I'll just write plus 2 times f of x1 plus 2 times f of x2 plus dot 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 plus 2 times f of xn minus 1 plus f of xn. Okay, so the sum will look like that. Okay, and we can break this into two separate sums. And the way we want to do that is we want to take everything that has a 2 in it, that'll be one sum, and then the two endpoints here we'll have as a separate sum. Okay, so you could write it like this. It'd be b minus a over 2n times f of x0 plus f of xn, okay, plus b minus a over 2n times 2f of x1 plus dot 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 plus 2f of xn minus 1. Okay, so that's everything in there. We've just kind of taken a couple of these and pulled them off separately. Okay. And then we can write this as b minus a over 2n. Let's leave this one alone. But then this other one over here we can simplify quite a bit, right? We can write plus b minus a over 2n times the sum I equals 1 to n of 2 f of xi. Okay. Okay. All right. So this, again, this is just kind of recapping here. All we've done is we've said, okay, we've got n trapezoids. Each trapezoid, the area can be calculated really easily as this. This would be the area of the first trapezoid, the second, the nth. Add all of those together. When we do that, we get this long string here, and then we can break it down into these two sums, basically. Okay. All right. Let's shift pages here. So then we're going to go ahead and let b minus a over n, we're going to let that equal delta x. And we can take the limit as n goes to infinity. Right? So namely, the number of trapezoids is going to increase without bound. And what's going to happen? Well, let's see. So we'll take the limit as n goes to infinity of, and let's just write it out up here so that there's no confusion, b minus a times f of x0 plus f of xn all over 2n plus the limit as n goes to infinity of this one, okay, which is, well, so what happens here? So here we've got b minus a over n. Well, so first of all, the 2's will cancel. Okay, and then it'll be b minus a over n, which is our delta xi. So it'll be like this. I equals 1 to n of f of xi times, instead of b minus a over n, it's delta x. Okay. All right. And so, very good. This is a Riemann sum. Right? So we know what that's going to be equal to. What about this other piece in front? Well, these b and a are constants. These are constants divided by 2n. N is growing without bounds, so this whole thing is going to equal 0. So this would be 0 plus this thing, which this is the integral, right? This is the Riemann sum. If n goes to infinity, the delta x drops to 0, and this basically becomes the integral from a to b of f of x dx. Okay, so this is basically kind of a derivation of how we can use trapezoids to basically approximate and then, generate an integral, a definite integral. And so this is all summarized in the following theorem. Right, so this following theorem is called the trapezoid rule. Okay, the trapezoid rule. So let f be continuous on the interval a to b. Then the trapezoid rule for approximating the integral from a to b of f of x dx is, okay, so the integral from a to b of f of x dx is approximately b minus a over 2n times f of x0 plus twice f of x1 plus twice f of x2 plus plus twice f of xn minus 1 plus f of xn. Okay, that's exactly what we just saw, right? That's the sum that we just saw. And as n goes to infinity, this right-hand side goes to the integral, becomes closer and closer in value to the integral. Okay, so that's the basically the trapezoid rule, and this can be used to approximate any integral. Okay, let's do an example. All right, example. Let's use the trapezoid rule to approximate this integral, 0 up to pi of sine of x dx. And we'll do it for n equals 4 and see what we get, and then we'll approximate it at higher for n equals something larger, like n equals 8. So if n is equal to 4, then delta x is equal to, it's going to be pi minus 0 over 4, or, pi over 4. Okay, so then the integral from 0 up to pi of sine of x dx is approximately, so it'd be b minus a. We'll just write it all in here. Pi minus a, which is 0, divided by twice n, which is 2 times 4. And then it's basically the function evaluated at each of the endpoints, right? So we start at sine of 0 plus 2 times sine of, well, I have to add pi over 4, so it's pi over 4, plus 2 times sine of, and I got to add another pi over 4, so that'd be 2 pi over 4, otherwise known as pi over 2, plus, and then this will be the last one. Oh no, not quite. So it'd be 1, 2, we need one more. So then I have to add another pi over 4 to this. That'd be 2 sine of, what would it be, 3 pi over 4, plus, and then this will be the last one, which doesn't have the 2 in front of it, so it'll be plus sine of, basically another pi over 4, which would just be sine of pi. Okay, and so we would get pi over 8 times sine of 0 is 0, plus sine of pi over 4 times 2 would be square root of 2. And then we get sine of pi over 2 is 1 times 2 is 2. And then this one over here would be, again, another square root of 2. And then sine of pi is 0. So altogether we get pi times, let's see, it's about 1 plus square root of 2 all over 4. And so all in, pull out a calculator and confirm this is about 1.896. Okay, so that's our approximation of this definite integral using just 4 trapezoids. Not a great approximation, probably, right? So what happens if we increase the approximation from n equals 4 up to n equals 8? What sort of improvement do we see, or should we expect to see? Well, let's see. Let's use n equals 8 next. So if n is equal to 8, then your delta x is again pi minus 0 over 8, so pi over 8 now. Okay, and it might make sense to just kind of write out all of the intervals. So we start at 0, and then pi over 8, and then another pi over 8 would be pi over, well, let's just write 2 pi over 8, 3 pi over 8, 4 pi over 8. So there's 1 interval, 2 intervals, 3 intervals, 4 intervals. 5 pi over 8, 6 pi over 8, 7 pi over 8, and pi. Right, so there's your breakout. And so then the integral from 0 up to pi of sine of x dx is approximately, it'll be b minus a over 2n, so that's going to be pi over 16. Okay, you just got to plug all of these values into sine. So sine of 0 plus 2 times sine of pi over 8 plus 2 times sine of pi over 4 plus 2 times sine of 3 pi over 8 plus, and twice sine of pi over which one are pi over 2 plus 2 times sine of 5 pi over 8 plus 2 times sine of 3 pi over 4 plus 2 times sine of 7 pi over 8 plus sine of pi. Okay, so a little tedious, right? But normally if you were doing this, you would be using a computer, and it would be very quick to do this. So I've done this ahead of time, and so I can tell you that when you just pull out your trigonometry unit circle cheat sheet and just like you're going to look up all of these values, and you'll see that in the end you get approximately 1.974. Okay, which is a different number, obviously, than the first one that we got. Now, in this case, there is an antiderivative, so we can actually evaluate this integral precisely. So sine of x dx, that's going to be equal to the negative cosine of x, evaluated from 0 up to pi. And so you get negative cos pi minus negative cos 0. And so what do you get here? You get negative... wait a second. Oh, sorry, the cosine here would be negative 1 minus negative, and then cosine of 0 is just 1. So this would be 1 plus 1, so 2. Okay, and so you can see we're getting closer, right? Even with just 8 intervals, we're relatively close, right? So obviously if you double that up to 16, you'd probably be good enough for most applications, perhaps. All right. Very good. So that's the trapezoid rule, right? This works for basically any integral, right? If you can't explicitly integrate, then you can you can fall back on this trapezoid rule. Now, what we're going to do next, we're going to explore one more technique, and this technique is going to be called Simpson's rule. This is a somewhat more powerful estimation technique. In order to use Simpson's rule, we have to have this following theorem. So let's look at this. So if p of x is a polynomial, and specifically a second degree polynomial, ax squared plus bx plus c, then, right, so if you have a polynomial ax squared plus bx plus c, then the integral from a to b of this px polynomial is equal to b minus a over 6 times p of a plus 4p of a plus b over 2 plus p of b. Okay, so let's talk this through a little bit. So the definite integral from a to b of p of x, where p is this quadratic polynomial, second degree polynomial, is equal to b minus a over 6. So take whatever the endpoints are, divide by 6. That's your out front coefficient out front. And then you want to evaluate p at a, the lower endpoint. You want to evaluate p at b, the upper endpoint. And you want to evaluate p at the average of the two endpoints, a plus b over 2, and that one gets 4 times that value. Okay, so this is somewhat. I mean, this is interesting, right? So this is basically saying if you have any quadratic expression like this can be evaluated without actually calculating the integral. Like you can just figure out what the definite integral is worth by plugging in this formula. So you might say to yourself, well, why would we ever want to do that? Because this polynomial is super easy to integrate, so why wouldn't I just do it that way? Well, generally you would do it that way, but what we're going to do is we're going to use this in our Simpson's formula. So this is going to be used in a coming formula. Now, in practice, this wouldn't be the ideal way to deal with a polynomial. You'd want to just integrate it straightforward. But let's this is a little bit of an involved derivation. It's a straightforward plug and chug sort of derivation, but it does involve a little bit of effort. But let's go ahead and run through the derivation. I may skip a few steps, but I'll give you the general outline. And then if you want, which I recommend, just pause the video and fill in the gaps. Okay. So the proof is going to be straightforward, a straightforward derivation. All right, so there's no crazy tricky algebra or anything. All we're going to do is we're going to say, okay, I've got a to b, px dx, and let's just integrate this. So that's going to be from a to b of ax squared plus bx plus c, right, like so. And again, this is just a polynomial, so we can quickly do this. It is ax cubed over 3 plus bx squared over 2 plus cx, and it's going to be evaluated from a up to b. Okay. So once we have this, then we can just, evaluate those endpoints. Okay. And so let's do that quickly. So we would plug, let's see here. Yeah, so we'd go ahead and plug that in. And so you can just do it this way. You can say a times b cubed minus a cubed over 3 plus b times b squared minus a squared over 2 plus c times b minus a. Okay, so that kind of gets you basically plugging in b minus a everywhere that you have an x. That's kind of another thing you can do with these definite integrals. I guess I never explicitly stated that, but maybe it was obvious. So once you do that, then you can expand this thing, and you can pull 1/6 out of this, and you get 2a times b cubed minus a cubed plus 3b b squared minus a squared plus 6c b minus a, like so. Okay, and then you can pull a b minus a out of this as well. Okay, now when you do that, you're basically, you kind of have to resort to sort of like polynomial division here and kind of divide this piece out of this. But I think if you do that, you'll see that what you end up with is a squared plus ab plus b squared here. And then when you do it over here, you get b plus a. This one's kind of obvious. b plus a times b minus a is definitely b squared minus a squared. And then over here, of course, you just get plus 6c. Okay, all right, so we kind of get to that piece. And then let's go ahead and expand everything. Okay, and when we do that, we get 2a squared plus 2a ab plus 2ab squared plus, and then expand that, 3b little b plus 3ba plus 6c. Okay, kind of do all of that. Now, the next, so it can be a little bit hairy, the next step, but basically what you want to do is you want to kind of group everything together, because remember, what we're trying to get to is this polynomial here, right? We're trying to get to, this grouping here. This is what we're targeting. We want P evaluated at A, P evaluated at B, and then this piece in the middle, right? And so what we can do is we can just kind of pull some of these apart. And so you've still got the B minus A over 6 out front. And we could grab one of these A times the little a's, squareds, right? And we can grab one of these, let's see, b times a, one of these here, plus b times a, and then we can grab a c. Okay, so this right here would be p of a. for example. And this just came from one of this first term came out of here. This second term, B of A, came out of over here, and then the C came out of over there. And you just got to kind of keep track of which ones you've pulled out and kind of the counts, right? But then you could do the same thing for P of B, right? You could go get P of B. It'll just be A times B squared plus B times little b plus C. And then this would be your P of B. Now, where did all of that come from? Well, the A times B squared, one of them came from here. And then the B times little b, one of them came from here, and then the C came from over there, right? And then you still got all the rest of the junk, right? So let's write down what's left after you do that. So you have A times little a squared plus 2AB plus A times B squared plus 2B little b plus 2B little a plus 4C. Okay, so again, it's as I said, this is a little. It's not like it's super tricky, but it can be a little involved, right? You just have to be a little bit careful to not drop anything. So B minus A over 6 still out front, and then you've got your P of A accounted for. You've also got your P of B accounted for. That's those two pieces. And what we can do is we can divide a 4 out of this, and when you do that, what you get is actually, let me hold on. I don't want to go to that yet. Let's scratch that. So let's gather up all of the big A's first, right? So I would have, this is going to be just a reordering exercise. So I have A times little a squared plus 2A AB plus A B squared, right? So there's that piece. And then plus, let's gather up all the big B's and the C here. I've got 2BB plus 2BA plus 4C. Okay, so just kind of shuffling a lot of things around here. Okay. And then I can do some factoring really quickly here. Right, so I've got, again, my P of A out front plus my P of B. Now, I can factor an A out of all these terms, right? So plus A times, and then it's A squared plus 2 little ab plus B squared. And I can factor a B out of those two. And I get, actually I can factor a 2B out of that. Plus 2 times B, and I get an A plus B there. And then I've got plus 4C on the end. Okay. Don't lose heart, we're very close. So P times P of A plus P of B plus, now here's where I'm going to pull, this is going to be kind of a funny sort of factorization trick here. I'm going to pull a 4 out of all of these terms, even though there's no 4 in there. Now watch what happens. I pull a 4 out, then I've got my A, and then this can all be factored into B plus A squared. Okay. And if I put a 2 down here, then that's 2 squared, which accounts for the 4 here. Okay. Now similarly here, I've got the B, and I can write A, but it's 2B, right? So I can write A plus B over 2. Okay, it looks like that. Looks good. Okay. And over here, since I pulled the 4 out, I just have the C. Okay. All right, so now what is this big mess here? What is that? Well, that's P. So this piece here is your P of A plus B over 2. Right? That's kind of the, we had to, in order to get it into that form, we had to do this sort of tricky derivation here. Now the whole thing then, just to sort of summarize, the whole thing is equal to B minus A over 6 times P of A plus P of B plus 4 times P of B plus A over 2. Okay, and that's basically what we needed. Okay, All right, so you can think that's sort of the end of the proof. Okay, so again, I know there was a little bit of a some sort of tricky stuff there, but as I said, it's just algebra, it's just factoring and you know, gathering like terms and all that jazz. So, but it can be a little tricky. So make sure you feel free, obviously pause the thing and make sure you understand each of those steps. Okay, so again, we're working towards Simpson's rule. Okay, so we're working towards Simpson's rule, and our goal is another version of a definite integral approximation. So here again, we're going to want to start by partitioning AB into n sub intervals. Okay, and then each of width delta x equals b minus a over n. Now this time, however, since Simpson's rule is going to require this time, however, n needs to be an even number. Okay, n needs to be an even number, right? And the partition would look like this: a equals x0 less than x1 less than x2 less than x3 less than x4 less than ... less than xn minus 2 less than xn minus 1 less than xn equals b. And I put some extra terms in here because basically we're gonna actually define double subintervals. So we're going to have this subinterval from x0 up to x2, right? And then we'll have another subinterval from x2 up to x4, right? And so on. And then we'll have this last one from xn minus 2 up to x of n. Okay, no problem doing this. We can do this. We just have to kind of have it at the front of your mind that these intervals, basically all we require is that n be an even number, 2, 4, 6, whatever, so that the double subintervals will actually exist. So then on each double subinterval, and we'll call it xi minus 2 to xi, okay, we can approximate f by a polynomial p okay, where p is of degree less than or equal to 2. Okay, right, so this would be a second degree polynomial or maybe a first degree polynomial. Okay, or potentially a constant. Okay. Okay, so let's draw a picture here so we can kind of see what we're up to. Okay, so let's see how great my drawing is going to be here. So let's say we've got some function that kind of looks like this. So this is our f of x. Okay, and then let's say I've got x0 here, and maybe x1 there, and x2 there. Okay, so the interval of interest is this one. I'll just put all three in there, okay? And so what we're saying is that it's possible to estimate this curve using a polynomial of degree 0, 1, or 2. In this case, just given the nature of the curve, a second degree polynomial would be a good choice, right? Because you can imagine, you know, you might have a second degree polynomial that comes down like this, comes up like this, right? That's just going to be a parabola. Okay, and so this would be your p, right? This kind of dashed line, right? It doesn't explicitly follow f, and f and p are certainly not equal, but on this particular interval, they might be very close. Okay. So just to put this into some more explicit terms here. So on the subinterval x0 to x2, choose the polynomial of degree less than 2 that best fits the points x0, y0, x1, y1, x2, y2, right? So those are basically going to be these 3 points. Okay, so you want to find some polynomial that fits those 3 points as precisely as possible. Okay, so right, so we're all kind of we're in good shape so far. So using P as the approximation of f, okay, using P as the approximation of f on this subinterval, from x0 up to x2. Right, we're just concerned with this one subinterval. So if P is our approximation, we can use the previous theorem to calculate what the area is on that subinterval, right? Exactly, precisely. Okay, and so we can say the integral from x0 up to x2 of f of x dx is approximately the integral from x0 to x2, oops, on the page here, of p of x d of x. Okay, so it's not exactly, right? There's going to be some distinction between the two curves here, right? But we're assuming p is the best fit for these 3 points. It's equal to these 3 points. Okay, maybe what's in between we can't guarantee, but those 3 points we know it's equal to those 3 points. Then this guy here can be evaluated as x2 minus x0 over 6, right? We just went through this, so it's p of x0 plus 4p of x0 plus x2 over 2 plus p of x2. Right, so that's just the theorem that we just previously looked at, right? Okay, very good. Then let's mess with this a little bit and see what else we can see. So this guy here is equal to, again, x2 minus x0 over 6 out front. And we've got the p of x0, and we've got the 4 times p of x0 plus x2 over x1. So what is this, though? This has a very precise value that we know. This is just x1, isn't it, right? x0 is on the x-axis, x2 is on the x-axis, and right in between, the average of those two numbers is x1 every time. Right, so this is just the average. Right, the average value is always x1 plus p of x2. Okay, so that's nice. Okay, so we've simplified things dramatically here, right? Using this polynomial thing, and then using kind of the fact that x1 is always the average of x0 and x2, right? In the case of the construction that we've built. Okay. So what else can we do here? Well, x2 minus x0, that's just b minus a over n, right? So let's put that in here. So we've got 2 times b minus a over n, right? So it's 2 times. It's x0 up to x1 is b minus a over n, and then x1 up to x2 is another one. So you got 2 of them, all divided by 6. And then you've got p of x0 plus 4p of x1 plus p of x2. Okay. And we can simplify up front here a bit, and we can write this as b minus a, and then the 2 and the 6 obviously would cancel, and the n would be down there as well, so you'd have 3n. Okay, now p of x0, right, we said that, let's write this over here, note, p of x0 is equal to f of x0, right? That's what we required of p, that it be equal to f at these 3 points. P of x0 is f of x0, p of x1 is f of x1, p of x2 is f of x2. Okay, so we can just, instead of using p, we can just plug f back in here, can't we? F of x0 plus 4 f of x1 plus f of x2. Okay, so what we have here then is actually a formula that takes this polynomial expression, this expression involving polynomials, estimating a polynomial, and because our f is approximately equal to the polynomial on the interval, then we can use that to come up with an expression that involves f rather than p, which is a lot more convenient, right? Because then we don't have to go and actually find a p, we just have to assume one exists and we can use this expression. So what we see here then is that the integral from x0 up to x2 of f of x dx is approximately equal to b minus a over 3n times f of x0 plus 4 f of x1 plus f of x2. Okay, and this can be repeated on the entire interval AB, right? So we just talked about one little double subinterval x0 to x2, but you could obviously do this for all of xn's. Okay, and so this summarizes, this can be summarized, and that summary is the Simpson's rule, and we'll write it as a theorem here. Simpson's rule. Okay, and this is technically for n even. Okay, so let f be a continuous function on AB, then, okay, the integral from a to b of f of x dx is approximately b minus a over 3n times f of x0 plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus dot 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 plus 4 times f of xn minus 1 plus f of xn. Okay, so you may be wondering, why did I put so many terms in here? Well, there's a pattern to the coefficients, and I wanted to kind of get that pattern in here a little bit. So we'll talk about that pattern in a second, but basically this is the approximation, and it is a fact that as n goes to infinity, the right-hand side of this expression, of this approximation, goes to the integral, right? The limit is the integral, as you can imagine, right? As the norm of the partition drops to 0, i.e. the number of intervals increases to infinity, then this basically turns into the integral. Okay. Now something to note the coefficients. They have a certain pattern. And so the first one is always 1, and then it's 4, and then it's oscillates between 2 and 4. All right, so like that. So if you had, well, so that's the pattern. Okay. All right. Excellent. Let's do an example of this. So this is a very powerful approximation. I don't, off the top of my head, know how much better it is than the trapezoid rule, but it is better than the trapezoid rule, and we can see that by, let's just take the same example that we did previously. Let's estimate the integral from 0 to pi of sine x dx, and let's just use n equals 4. So the integral from 0 to pi of sine x dx is approximately pi minus 0 over, well, it's 3 times n, so it'd be 12. Okay, and then it would be sine of 0 plus 4 times sine of pi over 4, right? So you're adding a pi over 4 each time, plus 2 times sine of pi over 2, plus 4 times sine of 3 pi over 4, plus sine of pi. Okay, when you plug all of that in, you get like 0 plus 4 times, and then the sine of pi over 4 is the square root of 2 over 2, plus 2 times, and this would be the sine of pi over 2 is 1, plus 4 times, and then again here's pi square root of 2 over 2, and then plus 0 on the end there again. And so adding all of these up, you get 7.66, and all together you get 2.005. All right, so even with only 4 intervals, n equals 4 intervals, you still get a very tight approximation. I think with the trapezoid rule, nothing wrong with the trapezoid rule, but we were seeing the trapezoid rule produced 1.89 using n equals 4. Okay, so this is obviously a little bit better. So yeah, so there it is. That's another technique that can be used to approximate integrals. All right, definite integrals. All right, so I think that's gonna do it for this section. This was, again, numerical integration, and so it just explored a couple of different ideas, ways to integrate when you don't have an antiderivative, right? When you don't have an obvious expression to evaluate the integral with. So, all right, then there's, as I said, there's lots and lots of additional techniques. This is, numerical integration is probably a course unto itself, right? There's all kinds of ways to evaluate integrals, but here are a few. The Simpson's rule in particular I know is very popular and useful. Trapezoid rule really goes back to the beginning of the whole idea of integration, actually. I think our initial motivating example, if you recall, was the circle, right, which you can kind of think of as, you can approximate that area using little triangles, which is a very similar idea to the trapezoid rule, right? Using trapezoids to approximate those little vertical slits, right? So, all right, well, we'll leave it there for now, and I will see you all next time. Take care.